So in general, what will happen? Let's say x1 plus x2 equals to 8, and the three lines don't intersect, and we have no solution to satisfy all three equations simultaneously. Yeah, so, well, what has this got to do with linear programming? Linear programming is to say, well, let's not insist on precision. Give some allowance, have some flexibility, right? So don't insist on equal, equal, equal all through. Let's relax that a little bit. Let's say we allow for room, all right? Anything that's less than equal to 6, all right, of course, let's also assume further that they are greater equal to 0. Less than equal to 6, less than equal to 36, greater equal to 1. Okay, don't insist on exactly equal to 1 or exactly equal to 8. Then can we find solution? So in real life, it will be that the boss will say, don't make more than 6 tables. Oh, sorry, 6 chairs, right? Don't use more than 36 labor hours and so on. So that gives space, as we can see in the graphical space here, this polygon, right, gives us all the possible points that will potentially satisfy the three equations. Well, in general, we also allow x1, x2 to be fractional, right? Even though, of course, when we apply to real life, number of chairs and tables uh, may be integer, but fractional chairs or tables per week is a rate of production, and we can interpret it as, for example, if x1 were to be 1.5, we can interpret it as making 3 tables in 2 weeks. And that kind of rate of production is always doable. And so it's not impossible to accept x1, x2 being fractional. So in that case, we find that any point, including the fractional points, in this polygon will satisfy all three inequalities, no longer equations. But then that is kind of nice because now we have a lot of possible solutions. Any point in this polygon will make boss happy, right? So example, make 4 tables and 1 chair. Let's check. Um, x2 is 1, that's less than or equal to 6. 4 tables 12 plus 4, that's less than or equal to 36. And 4 plus 1, 5, definitely greater or equal to 1, right? And you can check manually again, any points like 5, 3, 6, 0, make 6 tables, no chairs, 8, 2, etc., right? So long as the points all lie within this polygon, and you can see this polygon is very related to the lines before, because when we shift this blue line down to 1 over here, you find that the lines actually draw out the outline, the border of this polygon, this solution space. So if once it's flexible, then we can have solutions. But there's another problem. There are so many choices. Boss now says, being irritated, give me the best point, please. Don't just shove me all these possible combinations of tables and chairs. I don't have time to work out what's the best. Give me the best point. So now you are angry because, boss, you got to tell me how to evaluate each combination, right? So can you tell me what is the function to score the points? Like 4, 1, how high or how low is this score? 5, 3, how high or how low is this score? Then, and only then, can I compare objectively and recommend the highest or so-called best point to you. Boss says, you're right. So he says, attach 5 as the coefficient for x1. So each table gets $5 profit, each share gets $2 profit, and 2 becomes the coefficient for x2. Give me the point that scores the highest profit. And that sounds familiar, right? So we want to max 5x1 plus 2x2. So this objective function is then applied to each and every candidate within all points in this polygon, and it turns that point, the xy coordinate, into a number. Because if you plug in 4, 1 into 5 times 4 plus 2 times 1, you get 22. And if you continue to do that, every point becomes a number, as you can see. And obviously now, and objectively, we can say $44 is the highest. How do I get that? Oh, you just make 8 tables and 2 chairs per week. I assure you, you'll get that profit, which is the highest because we have scanned through the viable scenarios, and only this point gives us the highest. So that's great. We basically have found the highest point. But wait, we're just kind of randomly drawing up 8 comma 2. How about any assurance that it is the best in the entire infinitely many points in this polygon? That is exactly what we want to do in linear programming. All right. So with that in mind, we can then come back to our example LP model like this and begin to draw out, all right, the solution space. What I've shown you just now is a kind of a graphical situation that has already been drawn out. You can see them, you can compare them, but how do you draw out from scratch? And that is what we're going to learn next. Yeah, so we'll go step by step from a blank sheet of paper, literally, and hopefully, if you stay with me, we'll eventually come up with this polygon and this line here and learn how to associate each graphical component to the parts in the LP model on the right side. Let's get started. So I hope you remember the uh, model. Where's our model? Let's write down our model again quickly. To adjust this a little bit. Okay. So we have max of 5x1 plus 2x2, x1 less than equal to 8, x2 less than equal to 6, 3x1 plus 4x2 less than equal to 36, x1 plus x2 greater equal to 1, and of course the two non-negativity constraints. Okay, so I hope you just keep this model with you because I want to put it in the corner and not have it block our drawings. Okay, so to begin with, we need to have, well, literally, we need to have x1 and x2. There's no requirement that x2 must be the y-axis. So if you prefer, you can actually, of course, just draw x2 in the x-axis. All right, we have x1 and x2. Then we need to quickly come up with some coordinates. So let's just call it 10 here. Therefore, 5. Um, okay. All right, so we have 6, 7, 8, 9, 0, 1, 2, 3, 4. And, well, I'm just going to do a rough sketch. You see, I don't really use measurements, not just because I want it to be quickly done. Uh, I do use ruler to make sure that the y and x axis they are straight. But other than that, it is more an illustration to get an idea of how we can find the solution in graphical form. Okay. So let's to draw the graphical solution of the given LP model. What you need to do is to look for the easiest constraint first. So we focus on the constraints and kind of don't worry about the objective function until the end. So the constraints will give us the polygon that we saw earlier on. And out of so many constraints, we'll pick the one that is easiest to begin with, right? The easiest is, of course, the non-negativity constraints. X1 greater equal to 0 means anything that is negative, X1 is negative, we don't have to consider. Okay, we will cut that out. X2 greater equal to 0 means anything X2 that is negative, X2 equals to -1, -2, -3, we don't want that. We only want positive X2s. So far that's the two constraints. And you notice that when I cut them out, I literally restrict the feasible region to only the first quadrant, the top right quadrant, the positive or rather non-negative values of X1 and X2. And we can continue to do that, right? Because we have the next two easier constraints, x1 less than equal to 8. So that is saying that if you turn that into an equation, x1 equal to 8, right? As a tool for us to draw the line first, the boundary first, then we'll have this. We'll have x1 equal to 8 in that sense. So this is x1 equals to 8. And we need to now, every line that we draw will kind of divide the remaining plane into two sections, not necessarily equally large, but they're both kind of infinite. So do we want the right side of x1 equals to 8 or the left side? Now, this is easy to check because if x1, for right side, x1 will be 9, 10, 11, 12. They are all larger than 8, right? And that doesn't match with the original inequality. Whereas x1 equals to 7, 6, 5, 4, that will fit the inequality. So we will therefore discard the right side of the plane. And so we'll just do that. So far, okay? And now you can work out the other inequality, right? So first step, we change it into an equation. Then we draw that line equation. And to draw that line is very easy, fortunately, but we'll see in a more difficult case later on. So x2 equals to 6. Any point on this line will have x2 equals to 6. Now we need to decide, do we want to discard the top or discard the bottom, right? So again, as you try out yourself, anything above the line will be x2 equals to 7, 8, 9, 10, really not matching the original inequality. So we're going to discard that. All right, easy enough. And of course, we should check, but it is obvious that any points below will match this inequality. Now, remember that as we draw and discard, we're actually intersecting all the remaining or the retained regions on the plane. So that's why we see now a very clear delineation of this rectangle formed by these four constraints, the two non-negativity constraints and x1 less than equal to 8, x2 less than equal to 6. We're not done, right? But so far we can see that every line that's being added cuts the plane to two sections. We got to throw away one section and retain the other section. Point number 2, every line that we draw creates one more vertex, one more corner, if you may. All right, so it will create one more corner. So far we have 4 constraints and we have 4 corners. Make sense? Yeah. So, and that is generally true unless we have special odd cases like redundant constraints, that basically don't describe additional information. Then of course it won't make sense. But assuming we have a very practical, generic, reasonable model, then this is always true. Adding a constraint will create another corner, another vertex.